The title of my presentation is Supporting Students' Understanding of Linear Function, a Review of the Literature. The purpose of this presentation is to review historical and contemporary literature on the use of the graphing calculator, specifically the TI-83, TI-84, Casio FX 1.0, and Casio FX 2.0 Plus series, on students' learning of the linear function depicted by graphic, tabular, and algebraic representations, and to discuss the major themes that emerge from the literature. The National Council of Teachers of Mathematics called for curricular reform and suggested there be a greater emphasis on the function concept for grades pre-kindergarten through 12 in their 1989 and 2000 documents. The concept of function is foundational and central to secondary and undergraduate mathematics. It is not only integral to understanding more rigorous facets of the discipline, but pivotal in understanding the connectedness of symbolic and graphical representations. Functions and graphs represent one of the earliest points in mathematics at which a student uses one symbolic system to expand and understand another, Lienhardt, Lasky, and Stein. Situated in sociocultural theories of learning emphasize the effects of context, environment, tools, and socialization on the development of schema, outcomes, and products of learning. Graphing calculators, as mathematical tools, serve as mediators of students' learning. Because the graphing calculator is readily available in most classrooms, it is important to explore how students use the tool to conceptualize meaning for linear functions. The literature discussed the affordances of the graphing calculator and how it was used to conceptualize the meaning of and for linear functions. Major themes that emerged from the literature suggested the calculator supported trivialization and inquiry and provided access by reducing the cognitive burden of the user. The graphing calculator trivialized the production of graphs, requiring little intricate knowledge on behalf of the user, and increased the speed and accuracy of production compared to traditional paper and pencil methods. Because the graphing calculator amplified learning, it allowed students to engage in the investigative process of observation, conjecture, proof, implementation, and application within the context of real-world-based problems. Again, the graphing calculator performed algorithmic and algebraic processes automatically, so students without requisite knowledge were given access and opportunity to consider more lofty mathematical ideas. The graphing calculator helps students to conceptualize meaning for linear functions and cultivated covariational reasoning by supporting students' transformation, visualization, and modeling. Students use the zoom feature and the multiple representations feature of the calculator to interpret graphs, to compare graphic representations in data sets, to solve linear functions in one variable, and to solve systems of linear equations in two variables. The graphing calculator allowed students to see two representations simultaneously. By changing the mode to horizontal or graph table, students were able to see the graph and table or graph and symbolic form of linear functions at the same time. In the literature, students use the zoom feature to identify x and y intercepts of linear functions and to find the point of intersection of a system of linear equations. For example, students were able to take a visual approach to solving the system y equals x and y equals 2x plus 4. Students use the zoom feature to find the point of intersection. The literature does not discuss the students using the trace feature or the calculate feature to find the points of intersection when solving systems of linear equations. Also, students analyze the fit of linear models by using the scatter plot and list features of the tool. Students were able to answer questions like, does the graph of y equals 3x plus 1 fit the data set of 0, 0, 2, 1, negative 6, and 6? By examining the intercepts, points of intersection, and fit of data through multiple representations, students were able to develop meaningful interpretations of solutions and to understand the connection between slope and initial values of a linear graph with the parameters of its symbolic representation. That is, students were able to analyze the role of the coefficient and constant in comparing graphs. Finally, the graphing calculator has several limitations as discussed by the literature. They include teachers' knowledge of technology, and teachers' knowledge in supporting whole group discussions, the limited dynamic motion and lack of color of the tool, and students' rote use of the technology tool.
In your pay, you start with $50 and get 9 every day. If you want to know over a year how much you get, calculating the graph might be your best bet. On the X, you measure it one day at a time, and your money gets tracked on the vertical Y. Now you got some, and you ain't even worked yet. $50, put it up, that's your y-intercept. After the first day, you got 59. Now you got 2 points, you can start drawing a line. The slope of that line, remember, rise over run. It's dollars over days, and you got 9 over 1. Remember, B, I think that's where we started at. $50 up on the graph, the y-intercept. And you know y equals mx plus b. Now you got y equals 9x plus 50. With a triple R sound. We're talking points and slopes, axes and origins. Y-intercept and quadrants, all for them. Rise up, run out. We mapping graphs to the triple R sound. We're talking points and slopes, axes and origins. Y-intercept and quadrants, all for them.
In conclusion, the graphing calculator is a powerful technology tool that supports students' trivialization and helps them to conceptualize linear function.